Hi, my name is John Krochmalny, and I've developed these visual tutorials to accompany any technical training format that might be delivered. In this presentation, single-phase electrical motors will be introduced. Also covered in this presentation are places one finds single-phase motors, how they operate, and how to do normal maintenance on them. There are 4 learning outcomes associated with this presentation. Number 1, describe inductance. Number 2, name electrical motor components. Number 3, differentiate between start and run windings. And number 4, reverse single-phase induction motors. It was Emil Lenz back in the early 1800s that discovered that when current passes through a conductor, magnetic lines of flux are generated and surround the conductors. As with any magnet, there are North Pole and South Pole orientations associated with these flux lines. The greater the amount of flux lines, the more powerful force of attraction or repulsion happens within the magnet. Placing another magnet in the presence of another leads to either an attraction or repulsion. In this graphic, we see similar poles of flux lines facing each other and therefore a repelling force. In the bottom bar magnet, we create a pivot that could cause rotation. Under this installation, we find that the rotational movement could happen as a result of the repelling forces of the flux lines. This is the operational principle behind electric induction motors. The power of a motor is associated with the number of flux lines generated in the motor coils, resulting in an increase in the repelling force. In single-phase induction motors, the current passes through the motor comes only from one direction per unit of time. In this case, all of the current comes from the L1 terminal and travels to the N terminal. Since we have 120 volts AC of power, this voltage appears and disappears according to the frequency of the AC power source. It is this difference in voltage pressure that causes the current to move through the circuit. Electric induction motors convert electrical energy into rotational mechanical torque to perform work. They are called induction motors because the flux lines generated in one coil results in a voltage induced in the other. If there's a difference in voltage in the induced coil, there will be a current flow in that induced coil, resulting in the generation of its own flux lines. All motors have similar components. When referring to induction motors, the major components are the stator, rotor, shaft, and bearings. The stator of an induction motor is the coil that is stationary. This coil does not move, but receives the current from the motor's power source. As current passes through the stator, magnetic lines of flux are generated. The leaving side current of the stator coil has the North Pole orientation of the flux lines. The entering side of the current in the stator has the south. As you can see in this graphic, the stator coil is a wound coil of copper conductor. This conductor is coated with an insulation that prevents short circuits happening when conductors touch each other. The rotor of the induction motor is the part that rotates under the influence of the flux lines. In this simplified graphic on the left, we see the opposing lines of flux that cause rotation. In reality, the rotor is also a coil. When the stator flux lines appear and collapse across the rotor coil, voltage is induced into the rotor. Because this voltage has a difference in value from one side of the rotor coil to the other, a current is generated. When this current flows from the higher voltage source to the lower in the rotor, it generates its own flux lines, which are in opposition to the stator flux lines. The rotation of the rotor results. Other key motor components include the shaft and the bearing. The shaft is locked into position in the rotor and rotates with it. Because there could be friction among parts that move, bearings are installed. These shaft bearings are lubricated to reduce wear. Some single-phase motors are built to produce more power for work. If the power of any motor is coming from the force generated by the flux lines, additional force could be accomplished by a technique involving splitting the phase. In this graphic, we see the flux lines of the stator coil impacting with the flux lines of the rotor. The split-phase induction motor utilizes a second coil. The first stator coil is referred to as the run windings. The second coil is referred to as the start winding. These two coils, the run and the start, provide for the extra flux lines needed for more repelling force and therefore increases the power of the motor. In split-phase induction motors, a capacitor is used. A capacitor is an electrical component having two plates that store electrons. As these electrons accumulate on the capacitor plates, the capacitor increases its voltage pressure. Amperage current, or the movement of electrons, causes the generation of flux lines in the run windings. It also builds the electrons on the plate A side of the capacitor. Since the plate B side of the capacitor wants to fill with the same amount of electrons, amperage flows toward this capacitor plate, causing the flux lines to build across the start winding. Maintenance on electric induction motors are commonly performed by technicians. As with any troubleshooting technique, it involves a process of what should be the original condition and comparing this to what the actual condition is. If the motor rotation needs to be reversed, the pathway of the current passing through the start winding is reversed. On the right side ladder diagrams, the top diagram shows a differing amperage pathway through the start windings compared to the lower diagram. Referring to the motor nameplate, we see that the motor manufacturer has designed this motor for a voltage of 120 volts AC. We can use this information to measure the voltage being supplied to the motor. The voltage configured meter is placed across the L1 and N terminals of the power supply. Notice that for all voltage measurements, the power has to be placed into operational mode in order to measure it. Also on the motor nameplate, we see the manufacturer's amperage value. If the motor has the proper load placed upon it, the motor's measured amperage will not exceed this value. In this motor, this properly loaded motor will not exceed 5.3 amps. If the motor draws more amps than this, it is said to be overloaded and a condition that needs to be corrected. Because of the higher amperages and possible shock injury, the use of clamp-on amp meters are used. These types of meters are positioned so that the conductor is within the jaws of the meter. The meter jaws measure the flux lines generated in that conductor as a result of the amperage and corresponds to an amperage scale. To determine if the run and start windings are open, we can perform a resistance measurement. As with any resistance configured multimeter, this test must be done with the motor disconnected from its power source. Placing the leads across R and C terminals, we should measure a lower resistance. Placing the leads across S and C terminals, we should measure medium resistance. A high resistance measurement would result in readings between R and S. If the meter measures an OL, or open line, there may be problems within the motor.